Hello, everybody. Um, so this is your introduction to quantum theory. I will tell you later what quantum means. But first, the reason why we're studying quantum theory is because we want to know the atomic structure. Okay, we want to know where the electrons are. Where are they? In this picture, you can see the results of quantum theory. It shows where the bright lights are is where the most probable location of the electron. Okay, the electron's location is very important because it helps us know about the reactivity of the atom. So, in order for us to study the electrons, we have to study light. And you guys were able to watch the Northern Lights and the videos about it, and you learned about it. And it's basically when particles from the sun, or gaseous particles that have a lot of energy, they're called plasma, hits the molecules in our atmosphere like oxygen, nitrogen, and carbon dioxide. For example, let's say this is an oxygen atom in oxygen gas. That energized particle makes the electron in the oxygen go up an energy level, and as it falls, it gives off a certain color of light, and that's the result of the Northern Lights. Okay? So, we will be looking at the nature of light and how it is due to the electrons falling and giving off radiation. We will be looking at atomic spectra. Each atom gives off a certain color of light because each atom have different arrangements of electrons. We will also be looking at matter and how it has wave and particle nature. And we will be looking at the quantum mechanical model of the atom, which tells us the probable location of the electron using calculus. Okay, so you guys read about fireworks, and you noticed that in fireworks they put different metals. The different metals give off different colors. And here are some of the colors that you saw in that video. Okay. The reason why each metal gives a different color is because each metal has different electrons in it. Since the electrons are different, or different numbers of electrons, different arrangements of electrons, then you get different colors. You get different energies coming out of that atom. So the question is, why did we get different colors, and where did the light come from? The light comes from moving electrons. Specifically, as it jumps from one energy level down to a lower energy level, it gives off a radiation. Okay? Or light in our case. Electrons, why do we care? We care because electrons are responsible for chemical reactions. And electrons are also responsible for why elements behave the way they do, their reactivity, or their properties. So if we want to know where the electrons are, we have to study light. So let's look into light. Light behaves sometimes like waves, and sometimes they behave like particles. Okay, so I will first prove to you that lights behave like waves. Okay, the first proof I'm going to show you is called a diffraction pattern. Okay, diffraction happens when light goes through a small hole. Because they're waves, some of the waves go on top of each other, increasing the intensity, and that's called when the waves are in phase. Then there is a constructive interference that happens, and that's when you see a bright light. So if you see here, when the waves are on top of each other, you can see the bright light. When the waves are out of phase, that means one's going up, the other is going down. What happens is they cancel each other out in a destructive interference, and you can see the dark spots. Okay, You've seen this happen before. You can see it when you close the door a little bit and let a little bit of light through. You can see the little lines. That is a diffraction pattern, and it's also proof that lights behave like waves. Okay, so since light behave like waves, we need to understand it. We will look at some properties of waves. The first one is called a frequency. The frequency is given by the symbol, like an idolized V. It's called nu. Okay? Frequency is the number of waves per second. The unit is 1 over S. So it's pretty much waves per second or per second. Or, actually the scientist, his last name is Hertz. A symbol is Hz. I don't like using Hertz because I like the seconds because it can cancel in the formula. Okay, so let's look at frequency really quickly. If you were surfing here versus here, you're gonna be feeling more waves over here because it has a higher frequency. There are more of them per second. Okay, so the wavelength is given by the symbol lambda, is the distance from peak to peak or trough to trough. Okay, either one is the same thing. Okay, so the longer the wavelength, you won't feel as many waves because they're so long, you won't feel the peaks. So it has low frequency. If it's shorter, then you feel more of them, so it has a higher frequency. So as the wavelength goes up, it gets longer, the frequency is not as frequent. Okay? The unit for wavelength is the unit for length, which is meters. Since it's really small, you see it a lot in nanometers. Okay? Now, all of this radiation, this is called electromagnetic radiation, and I'll tell you more later, all travel at the same speed. Okay? And that is only if they were in a vacuum. In a vacuum, that means there are no particles, like if they were in water or in the atmosphere. Let's say it's got molecules in the path, it might slow down the waves. But in vacuum, all light travel at the same speed, and that's the speed of light. So the reason it's C is because it comes from celeritos, meaning light. Okay, the speed of light is 3.00 e to the 8th meters per second. Okay, so the speed of light is equal to, there's a formula that relates these three, is equal to wavelength times frequency. Okay, let's see if this formula works. The speed of light is in meters per second, equals lambda needs to be in meters if you're using the speed of light as meters per second, and the frequency is 1 over S. As you can see that the unit works out. Also, the speed of light is a constant. It is 3e8. That means it will not change in a vacuum. Therefore, if the wavelength goes up, it's longer, it will not be as frequent. This has to go down to make it equal to the same number all the time. Okay? So let me talk about what electromagnetic radiation is. Okay? First, let's look at the words. Electro meaning electrons, and magnetic means magnet. You guys watched a video about making an electromagnet, right? The reason they put those two together is because every time you have a cord and you have moving electrons inside that cord, there is an invisible magnetic field around this cord. Okay, they always go together. It's just a law of nature. So every electric field has a magnetic field associated. That's why it's called electromagnetic. Okay, so An electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. So all this radiation that you're seeing has energy inside it. Okay. So the reason this is called a spectrum is nothing more than a range, maybe from small wavelength or long wavelength to short, a range or a list. Okay, so it's nothing complicated really. So let's go over here, radio waves. So the radio waves is very long. So if you're looking at an electron, that means it's probably coming from like a really small drop. It's not very energetic, it's not very frequent, it's very long. Okay, if you go over here to the end, let's go ahead and stop over here in gamma rays. Let's just visit the X-ray. You know that X-ray is radiation. All of these are radiation. Radio is radiation. Microwave is radiation. Light that you see is radiation. Okay, and this is the definition of it. It has energy propagating as a wave. The X-ray, though, comes from the atom as well, specifically the electrons, but this time it's falling from a really, really high energy level. So when it falls, it gives off a very powerful energy, and the wavelength is really, really small. It's so small that it's so frequent that it has very energetic. It has high energy over here on this side. That's why you are scared of it, because if this goes into your body, it has enough energy to knock off electrons from molecules, and it can break the bonds and cause cancer. Okay, so we protect ourselves from X-ray. Radio waves, on the other hand, it's not a very big drop, and it's not very energetic. So all this on this side are low in energy. Okay. Over here in the visible, all of these from here to the left, you cannot see, they're invisible. Here to the right, you can't see them either, they're invisible. Over here is the only visible, and that comes from a certain wavelength, and that wavelength is about 700 nanometers to about 400 nanometers are the waves that you can see. And the colors are as follows: red, orange, yellow, green, blue, purple. Okay, so the red is not very energetic. So if you see red light, it's not going to be as hot as a purple light. Unfortunately, we're not in the lab, but if you were able to see a Bunsen burner where it's giving off a flame, you're going to see a blue flame in the middle where the gases are being combusted over here. And you're going to see this is going to be blue, and this is going to be like an orange flame. Because the blue flame has a shorter wavelength in this area, blue and purple, this blue flame is like really, really short wavelength. It's a lot hotter than an orange flame because the orange is over here in the 700 nanometer range. Okay? Also, lastly on this, the gamma ray is so scary because that is actually coming from a nucleus. So inside the nucleus right here, you have protons, electrons, neutrons. Just protons, neutrons. And those protons, neutrons are also within it. It has energy levels in there as well. Okay, so when those protons, neutrons go up and down, they're also giving off energy, but a lot more than the electrons do. Okay, so that's the gamma ray. Okay, so to do problems, it's very simple. You will use the formula C is equal to wavelength times frequency. Okay, so C is always 3.00 e to the 8th if you wanted 3 sig figs meters per second. In these problems, they will give you one or the other, and they will make you solve for the other one. So a dental hygienist uses X-rays. Ooh, scary, right? Wavelength of 1.00 angstroms to take a series of dental radiographs. Okay, so let's just do that one problem. What is the frequency of that? So frequency symbol is a V. The way I remember these two is frequency. You can spell frequency with a V. I'm sorry. Frequency. That's how I remember it. because I get those confused, the frequency and the wavelength, the symbols. And the wavelength, I like, looks like an upside down Y, and I do this, wavelength. And that's how I remember those from each other, okay? So they're looking for the frequency for this one. The frequency is given here. And the wavelength is 1.00 angstrom. Sorry, 1.00 angstrom, okay? Here you can see that it needs to be in meters so it can cancel. So from our previous unit, we learned what an angstrom is. Okay, if you remember, one E10 angstroms is 1 meter. So 1 angstrom is 1 E negative 10 meters. Okay, that's 1.00 with 3 sig figs. Okay, so I'm going to plug that in 1.00 E negative 10 meters. And if they're looking for the frequency, you just divide by 1.00 E negative 10 meters to isolate that variable. So the frequency becomes, this cancels, the M cancels. You go 3E8 divided by 1E negative 10 is 3E8 minus 10 would be negative 18. Oh, I'm sorry, this should be 3 sig figs. 3.00 E negative 18, I think, right? Let me check. Okay, so that is the correct answer. 3 sig figs, 3 sig figs. I'm going to have 3 sig figs here, negative 18. So that means, no, it's not negative 18, I'm sorry. That doesn't make sense. It's positive 18. Because you can have, yeah, it's very frequent. This wave is really small. It's an X-ray, right? So you have a lot of it. 3E8, you don't have to write the positive. I forgot my rules of my exponent. You go 8 minus negative 10, which is 18. And this is meters per second, and the S stays, so it's going to be 1 over S. And that is the frequency of this X-ray radiation that the dental hygienist is using. Okay, let's try another one. So it says the patient's listening to a radio station. The wavelength is 325 centimeters. And looks out the window, and the wavelength for that one is 473 nanometers this time. What is the frequency of each one? What's the frequency of this one? Oops, frequency symbol is a V. A frequency, a nu. It's called a nu. And they want the frequency of this one as well. Okay, so 2 separate problems. Use the same formula. C is equal to wavelength times frequency. C is equal to wavelength times frequency. Go ahead and do the problems. Make sure you convert the units so they cancel. Pause the video and do it. Okay, so the here's the formula. I'm plugging in 3.00 E8 meters per second is equal to, the wavelength is, have to change this, centimeters to meters. 1 meter is 100 centimeters, so 3.25 meters. Plug that in here, 3.25 meters. And frequency is unknown. Solve for frequency, divide by 3.25 on both sides. The meters cancels, and you have 1 over S as your frequency. Okay, I got a really huge number. So I got 9.23 e to the 1, 2, 3, 4, 5, 6, 7. E to the 7 waves per second. Okay, let's try this one. Same thing, 3.00 E8 meters per second equals, change this to meters, 1 E9 nanometers is 1 meter. So this is 4.73 e to the negative 7 meters. So I plug that in here, 4.73 e to the negative 7 meters times the frequency. Okay, and then divide by 4.73 e negative 7 meters on both sides. The frequency would be equal to 6.34 e to the 14 1 over s, because the meter cancels. Okay, so if I look at all these waves, it looks like the X-ray is a little bit more, it's a lot more frequent because the waves are really, really small. As you can see, 1 e negative 10. Then the one that's not very frequent is the radio waves. I think this is the radio waves, right? So it's like very long, and the frequency is not very much. You don't feel the waves as much. Over here, this is the sky. So this is a light wave. So it's shorter than a radio wave. And it has a little bit higher frequency than a radio wave, but lower than an X-ray. Okay, and they are all electromagnetic radiation.